Students, everyone wants to live on top of the mountain, but all the happiness and growth occurs while you are climbing it. What I mean to say is that in your endeavor towards success, the steps which you are taking towards achieving your success are the most enjoyable one and are the most happiest moments.
Jai Hind students. So I hope you all are staying fit and you are fine and healthy, right? Welcome to my YouTube channel. In the previous lecture we have started with refraction, then we have discussed the laws of refraction, then we have discussed in detail regarding the refractive index, absolute refractive index, relative refractive index, factors on which the refractive index of a medium depends, and we have discussed the principle of reversibility of light as well, right? So let us recapitulate all those topics which I have done in the previous two lectures, right? So I have written these are the important formulas which you have already done. This is student as per Snell's law, right? Which is the ratio of sine of angle of incidence to the sine of angle of refraction is always constant, and that constant is known as refractive index. Refractive index of a medium with respect to air or vacuum is known as its absolute refractive index. And in terms of speed of light, it is defined as the ratio of the speed of light in air or vacuum to the speed of light in that particular medium. And in terms of wavelength, it is defined as ratio of the wavelength of the radiation in air to the wavelength of the radiation in that particular medium, right? This is the relative refractive index. Refractive index of medium 2 with respect to medium 1. So that in terms of velocity will be given by V1 by V2. In terms of wavelength, it is given by lambda 1 by lambda 2. This also we have discussed. Then this I have told you. Refractive index of a medium does depend upon the wavelength of the radiation. For different colors, a medium has different values of refractive index. For red radiation, for red wavelength, for red color, a given medium possesses minimum value of refractive index. While on the other hand, for violet, a medium possesses maximum value of refractive index. Understood? This is the consequence of principle of reversibility of light. This we have proved. Refractive index of 2 with respect to 1, it will be given by the reciprocal of refractive index of 1 with respect to 2. Students, there is another very, very important result, right? That follows from the refraction through multiple medium, right? I'll tell you the result. Suppose we need to find out the refractive index of glass with respect to water. We all are aware it is read as refractive index of glass with respect to water. It is absolute refractive index of glass divided by absolute refractive index of water. Absolute means with respect to air or with respect to vacuum. So this is the formula I am talking about. So this follows from refraction through multiple medium, which we'll discuss in the later section. So anyway, so refractive index of medium M with respect to medium N, it will be given by absolute refractive index of medium M divided by absolute refractive index of medium N. Right? Again, let's practice more. Refractive index of X with respect to medium Y, it will be absolute refractive index of medium X divided by absolute refractive index of medium Y. Absolute means with respect to air or vacuum. So this is another very, very important formula. So it is actually refractive index of medium 2 with respect to 1, it would be equal to absolute refractive index of medium 2 divided by absolute refractive index of medium 1. Right? So before we deal with the applications of refraction of light, before we draw various ray diagrams related to applications of refraction of light, we need to discuss few numericals, basic numericals based on these formulas. Right? So what we'll do is, let's consider a case where a light traveling in a glass. Light is traveling in a glass. Let's consider first example. Suppose light is traveling in a glass whose refractive index, absolute refractive index of the glass is given to be, absolute means with respect to air or vacuum. It is given to be 3 by 2. which is 1.5. So the refractive index of the medium is given. We are supposed to find out the velocity of the light in glass. This is to be found. We are supposed to find out the velocity of the light in glass. So for this, we will try to apply this particular formula. Absolute refractive index of a medium is given by ratio of the speed of light in air or vacuum to the speed of light in that particular medium. So V is to be determined. So it will be C divided by glass with respect to air. C is constant. C is towards the speed of light in air or vacuum. That is 3 into 10 raised to 8. This you should be aware of. This is a standard value. And what about the refractive index of glass with respect to air? It's 1.5. So it would be equal to 2 into 10 raised to 8 meter per second. So that will give you the speed of light in glass. One thing to be noted down is that in air or vacuum the speed of light is 3 into 10 raised to 8 meter per second. While in a glass the speed has reduced to 2 into 10 raised to 8 meter per second. So this numerical authenticates the very fact that the speed of light decreases when it enters a denser medium. So whenever light enters a denser medium, its speed tends to decrease. And when it travels from denser to rarer medium, its speed tends to increase. So this phenomenon of change in speed of the light or the phenomenon of bending of light when it travels from one medium to another is known as refraction of light. Right? So this is a very, very basic portion. Okay. Let's discuss the second one. Suppose students, the refractive index of glass with respect to air, I am talking about absolute refractive index. It's given to me 3 by 2. Also, absolute refractive index of water with respect to air, it's given to me 4 by 3. This is water and this is glass. Find refractive index of glass with respect to water. This is the relative refractive index. These are the absolute refractive index, and I have asked you to determine the relative refractive index of glass with respect to water. Right? And also, this is the first part, and second is water with respect to glass. Right? Let's do it. So let's find this one. As per the formula just now we have discussed, as per this formula, it will be equal to absolute refractive index of glass divided by absolute refractive index of water. Absolute refractive index of glass is given to be 3 by 2 divided by absolute refractive index of water is given to be 4 by 3. So it will be equal to 9 by 8. So students, always remember, glass over air is denser, water is rarer. So refractive index of denser with respect to rarer would be always greater than 1. Fine. On the other hand, refractive index of water with respect to glass, it will be equal to reciprocal of refractive index of glass with respect to water from this particular formula. So what do you get? It will be equal to 8 by 9. So water is the rarer medium, glass is the denser medium. So refractive index of rarer with respect to denser is always less than 1. Refractive index of denser with respect to rarer is always greater than 1. So which is the correct way of representation? It is always this one. That is, refractive index of a medium is always expressed. Refractive index of the denser medium with respect to some rarer medium. That is how refractive index is expressed. So in that scenario, the absolute refractive index of a medium or the refractive index of a denser medium with respect to a rarer medium is always greater than 1. Right? So this is another numerical based on these formulas. Now let's start with some applications. First is, you will do in your respective physics labs as well. It's an activity when light is incident on a parallel-sided glass slab in an oblique direction, then it bends. It shifts laterally or sidewise, and that phenomenon is known as lateral shift. right? So let's start with the first application, which is the lateral shift. This is the first application, lateral shift. Lateral means side, shift means deviation. So sidewise deviation of the light when it is made to incident on a parallel sided glass slab. So suppose this is a glass slab. Concentrate on the ray diagram, right? This is a parallel sided glass slab. It's a parallel sided glass slab. This is glass. Obviously, it will act as a denser medium. This is air. It will act as a rarer medium. So this is rarer, and glass, it will act as a denser medium. Now this is the normal, suppose. Now look, light is incident at this point in an oblique direction, like this. This will be the angle of incidence. Now suppose this glass slab is not present. Suppose it were absent. So in a given medium, in a particular medium, light would have travelled along the same straight path. So this dotted line indicates the incident ray when produced in the absence of any other medium. Light always travels along straight path in a particular medium. So in case the parallel sided glass slab is supposed to be absent, to be not present, in case it's entirely air or vacuum, then light would have travelled along the same straight path. So this is incident ray. This is incident ray when produced. When produced. Right? Now what happens is, it is rarer and this is denser. So what will happen? At point where refraction will take place, bending of light will take place, and as per rule 1, whenever light travels from rarer to denser, it will bend towards the normal, like this. It will bend towards the normal. So this one will be the angle of refraction. Again at this point, draw a normal over here. These two being normals are parallel to each other, therefore this angle would be equal to this angle. And at this point again refraction or bending of light will take place. Here light is travelling from denser to rarer, so it will bend away from the normal. So it will be like this. So this is incident ray, this is refracted ray, and this is known as emergent ray. It is known as emergent ray. And if you draw perpendicular over here, this distance will give you lateral shift. This distance will give you the magnitude of the lateral shift. And this angle is the emergent ray makes with the normal. This is known as angle of emergence. And by simple mathematics, by using Snell's law, it can be easily verified. For a parallel sided glass slab, angle I is equal to angle E. Right? So this phenomena is known as lateral shift. It's because of refraction of light. Again, I repeat, students. This is a parallel sided glass slab. When light is incident at a point in an oblique direction, then what happens? It laterally gets deviated. It sidewise gets deviated, right? And this is the emergent ray. So it should have followed this path in case of a single medium, but due to this glass slab, it is deviating its path, right? Its path getting bent, and it is laterally shifted. Its path gets laterally or sidewise shifted. And instead of following this path, it follows this path. So this phenomena, which is due to refraction of light, is known as lateral shift. And this distance, perpendicular distance between the emergent ray and the incident ray when produced, this perpendicular distance, that gives the measure of the lateral shift. So this is the first application of refraction of light. This is the first application of refraction of light. Right? Let's consider another example. Second application. It is normal shift. Now students, you must have observed, consider a water tank, consider a transparent water tank, and drop a coin. So what will happen? It will definitely sink and it will reach the bottom. When you view that coin from the rarer medium, when you watch that coin from the rarer medium, then the coin which is at the bottom will appear to be slightly raised up. So this phenomena again occurs due to refraction of light. and is known as normal shift. Normal means perpendicular. So its height is, its apparent depth is found to be less than that of its real depth, so that it slightly appears to be raised up. So I will explain this phenomenon with the help of this ray diagram. Please do concentrate. Suppose this is a water tank I am talking about. This is the surface, this is water. This is the water tank. Right, this is the water tank. Suppose a coin is placed over here. So obviously, this being water, it will be a denser medium. This is water. And this is air. This is rarer medium. Right? And this is the coin. So this will be the real depth. This is real depth. Right? This will be the real depth of the coin. This is the object. This is, suppose, the object. Let us consider it to be a coin. Now look, this is the object. Rays are to be emitted from the object only. So incident ray, as I told you, the ray which is incident normally over here from the object, it will remain undeviated. It will go straight like this. It will go straight. So the ray from the object which get incident on the interface normally, that will remain undeviated. This is the ray I am talking about. This will remain undeviated. While on the other hand, suppose this is point A and this point B, very close to point A. So drop a normal over here. Now what we'll do is, this is another ray. Incident on the interface in an oblique direction. This is the incident ray. This is the angle of incidence. This one is the angle of incidence. This ray is traveling from denser to rarer, so it will bend away from the normal like this. This is the angle of refraction. Understood now? Again, this is the object. From the object, the rays will get emitted. The ray which is normal, it will remain undeviated. But the ray which get incident at point in an oblique direction, since it is traveling from denser to rarer, it will bend away from the normal. So it will go like that. Right? These two rays enter the retina of the eye. Suppose the observer is here and is he intends to see this point, right? So these two rays, when it enters the retina of the eye, then it will appear as if these two rays are coming from a point somewhere over here. Produce it in the backward direction. Do produce it in the backward direction, like this. Produce it in the backward direction. So, these two rays, when it enters the retina of the eye, it will appear as if these two rays are coming from a point somewhere over here. So, this being the object, and here its image will be formed. Here its image will be formed. So, look, this is the ray diagram, right? In actual practice, for rays 1 and 2 to enter the retina of the eye, points A and B must lie infinitesimally, very, very close to each other. Very, very close to each other. But obviously, here some bending of light will take place. So when these two rays enter the retina of the eye, it appears as if these rays are coming from a point somewhere over here. So this is where the point will appear. This is where the point will appear, like this. So this is the apparent depth. Apparent means virtual depth. This is the apparent depth. And the difference between the real depth and the apparent depth, that is known as normal shift. This is known as normal shift. Right? So theoretically what I have told you is, when an object is in the denser medium and is viewed through the rarer medium, then the apparent depth of the object is found to be less than that of its real depth. Or in other words, the object, which in this case is a point, will appear to be slightly raised up. So this phenomenon which occurs due to refraction of light is known as normal shift. So mathematically, normal shift would be given by the difference between the real depth and the apparent depth. Right? So this is the second application of refraction of light. Both being the application of refraction of light. What about the third case? What about the third case? Third application. Let's see. just the opposite of this one, right? Here we have considered the case whereby the object is in the denser medium and the observer is in the rarer medium, right? Let's see what will happen if we consider the other case, right? Fourth example, third one suppose. Question is, to a swimmer underwater, try to listen to my question very, very carefully. To a swimmer underwater, will a man standing at the shore of a river appear to be taller, shorter, or of the same height? Right? So let's see. This is the water surface, and suppose this is the person standing over here. This is the person, this is the man standing over here. Right? This will act as an object. This is the person. This is suppose represented by A and B. And the swimmer is over here. A swimmer is under the water. When he sees this person standing at the shore of the river, then to this swimmer who is underwater, will the person standing on the shore of the river appear to be taller, shorter, or of the same height? So this situation is exactly the opposite of this. Here the observer is in the denser medium, which in this case is the swimmer, and the object is in the rarer medium. This is water and this is air. Right? This is rarer and this is denser. Here the object was in denser medium and the observer was in rarer medium. Here the object is in rarer medium, the observer is in the denser medium. So let's see. Suppose, let's consider these are the 2 points where the refraction is to be studied. So we can draw a normal over here like this. These are the 2 normals. Rays will come from the object. This is the object, suppose. This is the object. Right? So rays will come like this. This will be the angle of incidence. Suppose I1. This is another angle of incidence at the different point I2. I2 will be greater than I1 definitely. So what happens is, ray is coming from rarer to denser. So it will bend towards the normal. Like this. In both the cases, since the angle of incidence are different, therefore angle of refraction will be also different. So these two rays, 1 and 2, will enter the retina of the eye. These two will enter the retina of the eye, which is the swimmer in this case, right? These 2 rays will enter the retina of the eye. And to the swimmer, these 2 rays will appear to be coming from a point somewhere over here. So what to do is, reproduce or produce these 2 rays in the backward direction, like this. Produce these 2 rays in the backward direction. Because these 2 rays appear to be coming from a particular point, like this. So this point will appear to be somewhere over here. Let it be A dash. So look, this is the actual object. Rays are getting incident at 2 different points. After getting refracted, it will go like this. And these 2 rays, when enters the eye of the swimmer, it will appear as if these 2 rays are coming from a point somewhere over here. So this point appears to be over here. So as a result, what will happen? The person standing on the shore of the river will appear to be much taller than his actual height. So it's just the opposite. In case the object is in the denser medium, then it will get slightly raised up. So the apparent depth is less than the real depth. In case the object is in the rarer medium and is viewed through the denser medium, then it appears to be taller. Therefore, to a fish underwater or to a swimmer underwater, a person standing on the shore of the river will appear to be taller than he normally is. So this is again a very, very important, interesting application of refraction of light. Right? There is some other example as well. Look students, we are able to see the sun 2 minutes before actual it rises, and we can see the sun for 2 minutes even after the actual sunset. What I mean to say is that the total duration of the day get increased by a total of 4 minutes. Right? Again I repeat. We can see the sun 2 minutes before its actual sunrise and 2 minutes after the actual sunset, so that the length of the day elongates or increases by a total duration of 4 minutes. So that can also be explained with the help of atmospheric refraction of light. So let's see. So for that also you need to draw a ray diagram. Ray diagrams, students, they are very, very important. You need to practice these ray diagrams, right? So this is the earth and this is the observer over here. This is the observer over here. And this is suppose the horizon. This is the horizon. This is suppose the horizon. As you are aware, Earth's atmosphere is up to 400, 500 kilometers, right? As we go up, as the altitude is increased, the density becomes lesser and lesser, right? So what I mean to say is that near the surface, the density of the atmosphere is maximum. So suppose the sun is here. Let us consider the sun is below the horizon. So the sun is positioned somewhere over here. So it's at a very, very far away distance. So that is why I have shown it with a small circle, right? So sun is over here. So rays will be coming, right? These rays are going. So once it enters the Earth's atmosphere, it is traveling from rarer to denser. Rarer to denser. As it reaches near the Earth's surface, it will cross more and more pair of media from rarer to denser, then again from rarer to denser. So as it approaches the Earth's surface, the medium will become more and more dense. So accordingly, whenever a ray of light travels from rarer to denser medium, it tends to bend towards the normal. So actually, there is no particular boundary, there is no definite boundary. But actually what happens is, as it enters the Earth's atmosphere, it will keep on bending like this. And eventually, it will enter the observer's eye. So this bending will take place due to the fact that light is traveling from rarer to denser. And whenever light travels from rarer to denser, the light tends to bend towards the normal. So now it will reach the observer's eye. But for the observer, it will appear as if this ray from the sun is coming from a point somewhere over here. So this is where the apparent position of the sun would be. This is the real position. This is the real position of the sun. And this is the apparent position of the sun. Apparent means virtual position of the sun. So it is due to the refraction of light. Again, I am explaining this dotted line, which is the tangent at point O. This is the horizon. Now, let us consider the sun to be below the horizon. Even then, sun will be viewed by this observer because of the fact that the light from the sun, when it enters the atmosphere, it keeps on bending as it travels from rarer to denser medium. So as the ray enters the observer's eye, it will appear as if the ray is coming from a point somewhere over here. So here, the image of the sun is formed. So to the observer, it will appear as if the sun is over here, while the actual position of the sun is here. So there is a difference of about 0.5 degree, which is equivalent to 2 minutes. In time, it is equivalent to 2 minutes. So even if the sun has not actually rise, even then the sun is visible to us. So sun is visible to us 2 minutes before the actual sunrise. And similarly, even after the actual sunset, the sun can be seen by us for a duration of 2 minutes. Right? So in total, the duration of the day get increased by 4 minutes. So this, student, is again a very, very important application of refraction of light. So I hope we have discussed many applications, right? You will be able to understand the concepts once you go through it and watch the video again and again till the concepts are clear, right? We'll continue in the next session.